All right, so take a minute and go ahead and read through that example and then underline key features and draw a photo to represent what is happening in that diagram. Okay. So you can almost imagine that you have a poster with margins on the side that are left blank and printed material in the middle. So the margins on the side kind of represent the frame, or if you think about when you make a Word document, you have a bounded area with which your text is allowed to print. So it says the top and bottom margins are 3 centimeters and the side margins are 2. So we're actually told what these distances are in here. So that 3 and 2 don't represent the height of the poster paper, they represent the length or distance of the margins from the printed area. And then it says if the area of printed material on the poster is fixed, so area is fixed and it is fixed at 192 centimeters. So that means the area of the black printed region could be represented by x times y and has to equal 192. So we're saying that this length here is x and this length here is y. So the printed region is x by y equal to 192. Find the dimensions of the poster with the smallest area. So that means my outside dimension is x plus 4 because of the inside printed plus the 4 centimeter margin. And from top to bottom is y plus 6 because the 3 centimeter margins outside of the printed area. So that means the total area of the poster that we are trying to minimize would be x plus 4 times y plus 6. So the total area, or the area we are trying to minimize, is that x plus 4 times y plus 6. So once again, we're going to use our one formula to substitute in to another formula. So let's say in this case that I solve the top formula for y. I'm going to substitute or replace y in my total area formula, thus making my total area equal to x plus 4 times 192 over x plus 6. And personally, I like to FOIL and then derive, but you could do the product rule and derive while you FOIL. So I personally would probably multiply these in. So x times 192x, cancel your x's and leave you with 192. And then you get 6 times x, which is 6x. And then you get 192 over x times 4. So 4 times 192, we'll think of 4 times 200. That would be 800. But then 192 is 8 less, so you take 4 times 8 and get 32. So to take 4 times 192 mentally, you think of it as like 4 times 200 minus 32, which is 768 all over x, and then 4 times 6 is 24. What's nice about taking it this way and then taking your derivative is that the derivative of a constant is 0. So the 192 and the 24 are going to be totally gone when we take our derivatives. So I'm left with 6x minus, so that's kind of like x to the negative 1. So you get negative 768 over x squared, because you'd subtract 1 away. And then to get your common denominator, you'd have 6x squared minus 768 all over x squared. And we know that when total area prime, if the denominator equals 0, is when x equals 0. But we know that it would be illogical to have a width of 0. So we kind of toss that answer out. And we solve for 6x squared minus 768. So you get 768 divided by 6 equals x squared. And 768 divided by 6 is 128 equals x squared. And then you take your square root of both sides. And you get x equals plus, and honestly there is a minus, but what do we know about a negative? That doesn't really logically make sense for a length. So we get the positive square root of 128, which is approximately I can't do that math in my head. $11.313, or you could say 314 or 3137. So again, AP accepts 3 different answers: totally truncated, rounded correctly, or just 4 decimals truncated. So they would accept any of those 3 answers. And since we only have one answer, this is the answer that will make this the smallest. You could confirm that if you wanted by putting 11.3137 on a number line and comparing the signs to the left and to the right. So what I mean is if you plugged in something like 1, 6 minus 768 is in fact negative. And then if you plugged in something larger than 1, or larger than 11 rather, like 20, we know that 20 squared is 400, so then 768 divided by 400 is going to be a much smaller number than 6, thus making this side positive. So this does in fact decrease, then increase on the original total area, making 11.3137 the minimum dimension for my poster. So that represents the length of X. It says to find the dimensions of the poster. So the dimensions of the poster are X and Y added to our outside pieces. So the dimensions would be 11.3137 plus 4 by, and you'd have to take 192 and divide it by that value. Which is 16.97, and add 6 to that because of the margins. So you get 15.3137 by 22.9705 centimeters. Because once again, it was asking for dimensions. Anytime you do decimals, you need to have 3. Okay. So yesterday we looked at a formula from the past, kind of using our geometry formulas. Geometry formulas are coming back. They're going to come back even more when we do the next section, which is related rates. So it's important that if you maybe don't know them, you kind of go back and just look at a few of them. We're going to do all of them. So I'm going to go through like spheres, cylinders, cones, etc. So today is our first day looking at a cylinder. So it says a cylindrical can is made to hold 1 liter of oil. So a cylindrical can, if you recall from geometry, is consisting of 2 circles and a rectangle. So a cylindrical can in 3D looks like that. Flattened kind of looks like this. It's 2 circles and a rectangle. So if we're told it can hold 1 liter of oil, 1 liter of oil would represent volume. But we don't like to talk about volume in terms of liters because that doesn't give me a concept that we can relate to surface area or volume in terms of length with height type deals. So we have to change that 1 liter to centimeters cubed. So 1 liter is 1,000 cubic centimeters. And that's a piece of information they would typically give you in the reading or put at the end of the reading in parentheses. So that 1 liter equals 1,000 cubic centimeters is a piece of information they're going to maybe just like put at the very end. And you have to determine what to do with it. So it says to find the dimensions and amount of material that will minimize the cost of metal to manufacture the can. So in order to minimize a cost of metal to manufacture the can, we're trying to minimize the amount of material being used. So if you think about all the formulas I just talked about, we are trying to minimize surface area. We're trying to minimize the amount of material used to make the circle and the rectangle. So to minimize the cost of the metal, we're trying to minimize the surface area. So you have to know what the surface area of a cylinder is. And as I previously mentioned, it's 2 circles and a rectangle. So the area of a circle is pi r squared. So in this case, it's 2 pi r squared because I have 2 circles. And then the rectangle, we'll say that it has height h and radius r. So the circumference of a circle is going to represent the length around or the width of the rectangle. So the circumference of a circle will represent the width of the rectangle. So the circumference is 2 pi r. So that represents your width. So area of a rectangle is width times length. But we labeled the length as height h. So the surface area of a cylinder is 2 pi r squared plus 2 pi r h. And then we need to talk about volume. So the volume of a cylinder is pi r squared h. And in this case, we're told that it needs to hold a volume of 1,000 cubic centimeters. And we know that we need our equations to be in terms of one variable. So we're going to look at the volume equation and we're going to look at surface area and we're going to determine which variable we want to get rid of. And being that volume has a radius squared, I'm going to solve for h because I don't want to carry through a square root in my problem. So I'm going to say that h is equal to 1,000 over pi r squared. And then I'm going to take that h and I'm going to replace it in surface area. So that it becomes 2 pi r squared plus 2 pi r and then 1,000 over pi r squared. And much like we like to do, we would simplify that surface area. So the r's would cancel there, leaving you with just one r in the denominator. Your pi's could cancel as well, and you could distribute the 2 to the thousands. Thus making surface area 2 pi r squared plus 2,000 r to the negative 1, because you could bring up the r from the denominator as a negative exponent. We're trying to minimize cost of material, so we want to minimize our surface area. So we want to set surface area equal to 0 to find its extremas and take its derivative. So 2 times 2 is 4 pi r minus, because you bring down the negative on the r to the negative 1, 2,000 r, subtract 1 away, to the negative 2. Which is really like 4 pi r minus 2,000 over r squared. So to get that common denominator and to make this easier, we're just going to rewrite this over r squared, which makes my numerator r cubed. And once again, we can eliminate the denominator as a DNE because we know that r cannot equal 0, because we know that we can't have a radius smaller than 0. That's illogical. So since the denominator would only equal 0 for our DNEs, we can eliminate that because, again, we can't have a radius equal to 0, thus giving 4r cubed, or 4 pi r cubed rather, minus 2,000 equals 0. So you get 2,000 equals 4 pi r cubed, divide by 4 pi. Whoa. And we get r cubed equals 2,000 over 4 pi. or that r equals the cube root of 2000 over 4 pi. Which is approximately 5.419. So that gives the dimensions of the radius. That is also in centimeters. So honestly, it's probably pretty similar to an oil can you would have at your house for gasoline maybe. And then you need to also find your height. So the height is 1000 divided by pi times 5.419 squared, which is approximately 10.83. Actually, more like 10.845. Sorry, I tried to do that in my head. So we have our radius and our height. Okay. Questions on that? Because I know that was a lot. It's something you haven't really looked at in a while. Are we okay with where we got all of the geometric formulas? Can we understand conceptually, like, why we find our zeros and why we can eliminate the denominators? It all makes sense. Okay. So I believe that is the last problem we have for today, because then the next page starts into the business applications, which I'm going to save for Monday. I do have some helpful hints, and your homework is a little lengthy, so I want you to have some time to work on it in here. There is one more problem on your homework that I want to almost give you the diagram for, because it talks about describing how a pen is divided. So in the examples the other day, we had an example where we had the fencing and the farm. So I'm going to make up sort of an example that's similar to one on your homework. You don't have these helpful hints, but this is just something I want to talk about. If the function that you want to optimize has more than one variable, we go back to the days of substitution, which is actually what my Algebra 2 kids have their test on today. If you're not sure that the extreme value you found is the max or min as you were requested to find, you can always check it using our first derivatives number line chart, which is what we've done a couple times as well. If the endpoints could be a maximum or minimum, you have to check. So we haven't had a lot of problems where they've limited. We're going to have more of those examples on Monday. But remember that EVT still comes into play. So if we had been told that the radius could only exist from 2 centimeters to 4 centimeters, then that value we got would have been outside that, and we would have had to have checked our endpoints. So like I said, your homework is going to be back in your textbook. We already did some of these beginning problems yesterday. Again, we got kind of pushed back because of the 2-hour delay, so everything's a little, my PowerPoint's a little off because I readjusted. And I readjusted your Fusion homework due dates as well. So all of that's updated. But if you're given a problem and it talks about a farmer creating pens for its animals, and it says that there are multiple pens. So let's say I want to create 5 equal width pens, and I'm given like a full perimeter of, let's say, 1,000, then your drawing and your diagram, you need to consider 1, 2, 3, 4, 5, that you need 5 pens. Obviously, those are not perfectly even, but you need to consider that part of the perimeter is going to be used in these regions here. So if my entire width is W, my length is L, area is still length times width, however, perimeter is now adjusted in a way that it's 2W plus the 1, 2, 3, 4, 5, 6 L's. So you need to take into account that perimeter would use material to make those inside pens. Does that make sense? So I know we didn't actually find a problem where we did that, but that is an example of one of the homework problems you're going to have to draw a diagram for. And I just wanted to elaborate on the fact that the perimeter would get changed because of those extra lengths on the pens. All right. So if you want to borrow a textbook because you don't want to use the PDF on the computers, that's totally fine. There's some over on the wall next to Trevor, I believe, in those little cubby holes. And then you have the remainder of class time to work on these, ask me questions, get help. These are problems that definitely take some time. They also take drawings and pictures. So that's why I really want to focus and work on them today.